Right. Okay. Welcome everybody to the last lecture of the course, the most important of the course, because today we close the loop. Let's say we will define a controller to control the locomotion stability. This is an essential element in a locomotion framework because it allows to get the planet trajectory for the planner and create the desired torque to be sent to the low-level controller and then to the robot. So you see here a diagram of a typical locomotion framework like the one we use, and we have, for example, a user input that is a joypad that sends, or a navigation algorithm that sends desired velocities to the planner. Then the planner, given a map or in a heuristic way, works out the trajectory for the center of mass and for the orientation of the track. And these ones are transformed in a way that we will show. I will show you into torque commands, desired torque commands. The whole body controller, of course, needs knowledge of the state of the robot, so of the pose of the trunk and in the space. So we need a state estimation algorithm that can, for example, usually fuse exteroceptive information from a camera or proprioceptive ones from encoders, inertial measurement unit, for example, from encoders you get the odometry, which is an estimation of the velocity of the base that you integrate, and from the IMU also you can get an angular velocity that you can integrate, but that is prone to drift. So merging the two, you take the best of the two approaches and you try to find a better estimation. If you also add vision, estimating the visual flow, how the visual flow changes, you still have a third input that improves your estimation. So so as I said, the goal of the body controller is to compute the joint torques, and it has two goals. One is stabilize the trunk orientation. We see here we close the loop on the gyroscope of the IMU, and we are able to stand horizontal, go back horizontal whenever there is a push, even if the robot is trotting. So it's underactuated all the time on two legs, but still it can do some control on the orientation. And this other example is also to stabilize the center of mass, so orientation and control of the center of mass position. In this case, we have an arm, and if there is no control on the center of mass, this arm creates a big disturbance that makes the robot base completely move. Let me define locomotion stability, which is avoid falling and tipping over, and different from the classical definition of control stability. And in terms of locomotion stability, we can think about static stability as well. When the motion are very slow, that means that you can stop at any moment and don't tip over, be in equilibrium. So have the statics satisfied. And in general, static stability criterion is to keep the center of mass projection inside the support polygon. So if you have the stand speed, in the case of Quasi, if the center of mass is inside this blue area, we are sure that the robot is statically stable. If the robot, in the case of a Quasi biped, the flat feet, when you have 2 feet on the ground, create a support polygon of this shape, and again, if the center of mass is in this area, the robot is stable. But for this reason, because locomotion stability is related to somehow to the CM positioning, we want to be able to control the center of mass with our body controller. But let's first start simple, and we start from the controlling the base frame, and then we do an extension to the center of mass. The first approach is, the simplest one is a quasi-static approach, so it works, it's the simplest one, it works for the very slow motions, and also quasi-static motions, where you can neglect the influence of the joints dynamics and also the inertial effect, acceleration, Coriolis, and blah blah blah. And the idea is to compute the contact forces to produce the same effect at the fit, to produce the same effect of virtual forces and moment at the base frame. So we want to emulate virtual springs attached and dampers attached to the base frame. And we do that by applying a specific set of contact forces. These virtual elements that we attach to the base, they track a trajectory that is coming from the planar. So it's like, think about the rabbit, the donkey which is following the carrot, and then this attraction, this spring attracts the robot base and make it move. And the strongest the spring, the strongest is the attraction, and the prompt will be the reaction in tracking the trajectory. Then, how do we compute these virtual springs as we did in the case of the operational space? The same way we create a virtual force, but we attach the spring rather than at the end effector as we did before. We attach the spring at the base point, and we have a linear spring and a torsional spring that will create a virtual force and a virtual moment, and Vm. And of course, the virtual moment will be proportional to the orientation error that we saw. Then we stack together virtual spring force and virtual moment into a 6D vector that we call desired range. And what we do with this desired range, there are different ways to map this desired range into contact forces. The simplest one is a projection-based approach. So this was introduced back by 97 from Jerry Pratt. It's called virtual models. As then the works of the concept of virtual work, considering as an effect of the base frame. So instead of mapping contact forces at the end effector into torques, it maps wrenches at the base into contact forces. And this mapping is done through the JBT transpose matrix that we know, and we know that the mapping is this. So we can, from contact forces, project and get the range. Note that the contact force is living in a space which is k-dimensional, so normally it's bigger than the 6-dimensional space where it leads the range, the base range. Then, because we are in a spot, we are talking about quasi-static motion, we can have a quasi-static assumption, completely neglect inertias, so we can map these forces into contact forces back into torque. We can even have a gravity term here, which we cannot. You will find it in the next exercises. But how does JB transpose look like? This is called the contact range matrix, and we can retrieve writing the equation for statics, so equilibrium of force and moments. Should sum up to 0, so because there are 0 accelerations. In this case, we use again the skew symmetric operator to represent the cross product, and we have the skew symmetric matrix associated to the cross product, and we can write this equation this way. So we have the contact forces that sum up to the FVM and the moments that for each force sum up to the MVM, and this is JBT matrix, and maps contact forces into desired range. This is an example with 3 legs on the ground, so and in this case we have pure forces at the feet, so point feet. We have no moment at the feet, and this is the way it works. Think about a quadruped with 3 legs on the ground and point feet. So the first step is to map this desired range that we computed from the virtual stiffness and damper into contact forces. We got Syllabus because the size of this is bigger than the size of that, so we have redundancy, and we know that then we can map the forces again into torque. This is J matrix for how we define it. Usually note that there is a minus sign here because they are contact force, not an end effector force, so they should be the opposite when you link to torques. So very simple equation, just absorb inversion. However, the problem of this approach that we are not guaranteed on anything. So we know that these robots can only push and not pull on the ground. With this controller, we cannot enforce this. Ideally, you can even require negative forces in some situations. So for the Z component. You cannot even enforce friction constraints, so to avoid slippage, for example. Because, in essence, what this controller does, it finds a mapping on the 4 feet. So let's say this is the branch, which is like a gravity branch. So no angular component, just a force. And you will find 4 forces that are like this. And if you have a pseudo-inverse, Moore-Penrose pseudo-inverse, you will find a minimum norm force that provides this branch. If you multiply for GB transpose.
So you can still have positive forces.
Huh?
If you do that, you can have positive forces which are not real, right?
You might have negative forces. So if you think about this branch going out of the polygon, to have statics, you need negative forces. Let's think you are like this, the situation is like this. And to equilibrate this branch, you need this, but you need this. Okay? And this controller will require this. This is not possible.
So actually, for this out of the support area, then you will have this negative forces.
Exactly.
Okay.
Exactly.
But that's physically not possible.
No, because you require to pull on the ground, you grasp the ground, or you stick on the ground. You could do if you have a bilateral contact. Let's say you are glued to the ground, so you can do whatever you want if you are glued to the ground. You stay there, you pull from the ground, and you can stay out of the polygon. There's no problem. You can still exploit some redundancies to get different solution, setting a different weight on the pseudo-inverse, so you can get I don't know, this solution. You can get this solution because you still have a null space component, and you can play around adding tangential component that nullify each other. But we'll see that later on we want to add some friction constraints, some unilateral constraints, and you will see that that's the reason for which we moved to the QP based controller. We forgot to talk about the center of mass because we want to control locomotion stability depends on the central mass, and we want to close the loop on the central mass. So we see how do we do the derivation from the base to the central mass to extend it. And this is very important whenever you have a decentralized load. Think about like a center that has an arm. So you have a quadruped platform, and you have a heavy arm that is even collecting a weight. Let's say. And this weight shifts the central mass of several centimeters, up to even 10, forward. So if you control the base and you apply the gravity compensation, you don't know, ideally you should apply the gravity compensation always in the central mass at least. So you need to know how to do that. Ideally, you can control the base, but the stability is related to the central mass. So you don't care about moving the base point, you care about moving the central mass point inside the polygon. So here the central mass is very close to the polygon boundary and very little robustness, even though the base seems in the middle, right?
How do you estimate the center of mass? Only with the parameters of the robot, or
yes,
measure with anything?
There are, you can use the forces. You can use the forces. You can see when a robot is still, there is a paper I wrote in 2017 that moves your estimation of the central mass such that till explains the contact moments given by the forces. You know that the forces in static should have contact moments to 0, and with respect to the central mass, let's say you can write this with respect to the central mass. This is F. And so if you elaborate on this equation, you can find an expression for the central mass, an estimation of central mass, what the central mass should be for these contact forces. Okay, and then since doing an estimation in one step it's noisy, I use this to update the actual as a direction to update my actual estimation to the real value. So it will move till in a recursive way till you will reach the estimation. But it's written in a paper on load identification of 2017. We did this work. It's quite okay. The problem is that it relies on the contact force estimation. So if you're modeling error in the contact force estimation, you have inaccuracy in the central mass estimation. So ideally, if you have a good CAD, you should be able from the kinematics to compute it. Then the idea is to rather consider the fit in the computation of JB, consider the fit position with respect to the central mass. Before was like, this is central mass, sorry, let's see. Before we had xy phi, now we have xy phi minus c. So we write a moment about that. And the JB matrix will become JCOM and looks like this. We know that the equilibrium of forces doesn't change because only the angular part changes if you move the pole where you compute the moment about. Then we said we don't have a friction constraint, unilaterality constraint, so we move to a QP optimization approach to enforce these constraints. So look at this video on the top right, and you see what happens. while in the bottom one, the robot is able to traverse. So what is the difference between these two videos? What changes in the algorithm, in your opinion?
Could you repeat it? Friction constraints.
Exactly, friction constraint. This was just a constraint in Inv Dynamics for this robot without any optimization, and this was a QP problem where we optimize for contact forces and we incorporate friction constraints. So we were able to set the cones normal to the walls and have the forces always inside these cones and avoid slippage. Because for a robot with point feet, the surface is very small, so it's more difficult than for a human to work in such a environment. And the same here. Look what happens in the top one. These are like slippery patch. Think about the pieces of ice of different slipperiness, different coefficient of friction. Again, here we see that before the cones were always the same size and way bigger than the friction coefficient needed to traverse the patches, but here the friction cones is adapted and estimated. I wrote a paper on that, on how to estimate for slip detection and estimation. That allows to online estimate the friction coefficient and even the normal. So the forces are kind of moving out of the cone because the controller doesn't know that the cone is so small, and so the foot, as long as this happens, the foot starts to slip. Here, the robot has a cone big, then it immediately detects the slippage, a micro slippage, reduce the cone to the real one, and then the force stays into the real cone, and there is no longer slippage. Again, here there is no optimization of contact forces, and here the contact force estimation is optimized.
What is the blue line?
What?
The blue line that sometimes appears.
The blue line, it's estimation of the normal.
Okay.
It was a normal estimation. It will appear in a ramp whenever you need to complete it. The normal is always vertical, so
Okay.
yeah. The idea is to cast the control problem as an optimization problem with contact forces as decision variables, and then exploit this redundancy that we have to enforce these friction cone constraints. So think about, you can have forces vertical or horizontal, you can have whatever force, and you want to select the ones that satisfy the constraints. And to do so, we cast the control problem as a optimization problem. At the cost of this optimization problem, we write as a two-norm, Euclidean norm of the range error. We have the design range we want to tract, and we have the real range that is related to the contact forces, and then plus we have the regularization term that is needed to make this problem solvable. Because if you look the action of this matrix in the QP is not positive definite, because this matrix is a null space, and I will talk about that afterwards. Plus, we want the physical contact satisfied. And pay attention that the vector of forces are just the forces that are in contact. so related to the legs that are in stance. We don't use the whole body controller to set the torques and the forces for the leg in swing, unless you don't explicitly write a task for that. Okay? So in this case, we just have one task to control the center of mass or the base, in this case the base, and we don't care about the swinging leg. So the dimension of JB transpose will change. If I have 4 legs on the ground, it will be 12 rows, 12 columns. If I have 3 legs on the ground, we will have 9 columns. If you have 2 legs on the ground, we will have 6 columns. So you need to take care of the code. The contact state changes. Now, what physics dictates? We already saw this briefly in the early lectures. There are some limits on the tangential forces to the contact, to tangential force component of the force tangential to the contact surface, and this is using the friction Coulomb model. We saw that it can be written as a friction cone wherever you have the norm of the tangential component lower than a certain proportionality to the normal component, and where this proportionality is represented by the friction coefficient, that is in essence the size of the cone. So smaller friction coefficient means the smaller cone and smaller possible viable tangential forces, and bigger friction coefficient it's a bigger cone and a bigger possible tangential force. And this is whenever the robot is on non-slipping contact situation, so velocity of the slippage is 0. But you can have also the slippage condition. In this case, we said that the force, the Coulomb force, remains constant, and the force, the contact force is only the Coulomb force. We discard the viscous effects, and the force direction lies on the cone, that is opposite to the direction of slippage. So we have this definition for the tangential component is opposite to the velocity. This is the direction of the velocity vector during slippage. We don't care about this. We mainly talk about this in this course. So we call it friction cone constraints. While and to do friction cones, to write and code friction cones, we can use different ways. The most correct one is using second order cone constraints, but this is making then it becomes no longer a QP, the decision problem becomes a second order cone problem, which requires special solvers to be solved. So in general, what people do in robotics, they linearize the cones as pyramids, and you can use as many edges as you want. Now here we have 1, 2, 3, 4 edges, but you can have 8. And for each edge, in essence, you think about the cone. Inscribe the pyramid, yeah?
Why don't we use the second order cone programming in robotics? Is that a specific reason? Just because of difficulty?
Yeah, I think it's I mean, to use specific solvers. There are many QP solvers. It's easier to code. I'm not sure about the speed, if it is lower or not. Certainly, it is more accurate, but it becomes a different problem. So it's a bigger class than QP. I know Patrick Wensing is doing that. I just see that 90% of people use this pyramid approximation, and the approximation is that so in this case you have the friction coefficient is mu, so you need to compute the mu the divided by square root of 2, because you want to define this this constraint. So let's say we are considering this slice in this plane, and we see that here we have to have the friction force inside here. The force will be in this quadrant, and in this case, this inequality constraint holds. So this is mu over square root of 2, of course. And if it is in this quadrant, then this other inequality holds. While in the other direction, in the other slice, we have the same thing for the y component, positive and negative. So with all this, we have sure that we have the polytope pyramid approximation and as a constraint, and that the force will be inside this polytope, that is this pyramid. And this pyramid is an inscribed approximation of a cone. To write this in matrix form, we need to use as usual, the versor, the unit vector that represents the frame, the compact frame. So let's say you have a tx, you have a ty, tx, and n. So whenever you have a force, you project to n, and you get fn. You project to tx, and you find fx, and you project to f1, and you project to like this. So from this. Fy and fx. So doing the cross product, the dot product, sorry, you project on each one of them. So to write this, in essence, you can write this into this form. Just fx, which is f projected there, mu and transpose, which is fz. You see, and this is the what we call the friction constraints matrix, AFC, and we use linear optimization problem. The other constraint is a unilateral constraint. We said that the z component should be positive whenever the contact is established, and this is due to the fact that the leg can only push but not pull. There is no penetration, and are called unilateral constraints. And we know that we can implicitly enforce this constraint with the friction cones, because if the force it's forced to be inside the friction cone, it's forced to be in this half plane as well. So the unilateral constraint is naturally encoded, and you don't have to re-implement it and add additional constraints. You know that the unilateral constraint can also be written as a complementarity constraint, wherever you have this product to be zero between force and contact position. So this is the contact pz, the contact position, the distance of the end effector from the surface, and whenever this distance becomes zero, then f can be positive. Otherwise, if this is out of the contact and different than zero, then f is forced to be zero. But this pathological if we are using both fz and pz as decision variables. which is not our case now. So just for completeness, I say that. But in optimization, many people try to implement this and they find some problems because of, remember, the non-convexity of the constraints. So an important point, we talk about unilaterality constraints, so we want a force positive, but we might want also to control the loading of the leg. For example, if you want to move and start to swing, we want to first load the feet in stance that are not to swing and unload the force that is on this foot that I plan to swing. Whenever the force is 0, then I can remove it from the set of contact forces and start the swing. This way we avoid the torque discontinuity, because if you change the size of the JP matrix and you didn't do any unload, now immediately, bam, you will feel like, bah, and you create a discontinuity in the joints. So unloading the force is very good for the structure of the robot, for the mechanics, and normally you do a spline, you do a polynomial on the constraint itself. So on the you remember the AC matrix. In this case, you need to specifically enforce the unilaterality constraint, and which will be like this, and you would say that it's lower than F max and bigger than 0. So you have this F max that changes with time, and then we need to express explicitly a constraint on F delta. So to summarize, this is how the QP quasi-static problem looks like. We added a selection like a matrix S, a weighting matrix that allows you to select whenever you have some feasibility. For example, you are hitting the cones, you need to give up to the cost. You cannot drive it to 0. So it allows you to select which direction of the branch you care most in case of feasibility. Still have regularization, and then once we got the optimal forces, as in the projection case, we compute the torques. This time we can add some gravity compensation because we are still quasi-static, but we want to compensate gravity. Yeah, and as I said, this selection matrix can be useful in case of feasibility or under actuation. Whenever we cannot achieve somehow the desired range. It's important to think about. So this gravity here, it's the gravity of the legs, because this is JCQ, so this is living in JCJ, is in the twitted space, while we need to add gravity also to the robot as a whole to compensate the whole mass of the robot. So we know that gravity can be thought as having an application point located at the COM, and we want to apply a branch desired that is able to, on top of a feedback term, to provide a feed-forward gravity compensation, creating a branch compensating opposite to this one. Depending on wherever we define the controller at the base frame or at the COM frame. If you are at the base frame, we know that we have the linear, plus you have also the angular part, because this gravity will create a moment about this point, so we need to compensate also this moment.
Sorry, one question, but if I put the wrench for the gravity here, do we have to add also in the torque later, or just moving the stuff? Because in the slide before there was JTF computed from the QP plus the gravity compensation. But if I consider the gravity compensation inside the wrenches, the optimal forces are already compensating gravity, or I have to add in the torques anyway?
So the gravity I'm talking about, remember the floating base equations, for example, the coupled ones. If you write them in the base frame, NJB and J, you remember that you have HB or GB, HJ, right? Plus JB, J transpose. So these are the ones that we compensated, the gravity part that we compensated there. And this is the gravity that we compensate later on. We know that if we use the centroidal thing, that we show that these terms disappear, so you don't need it. But in this case, we are doing yeah, it's a good point.
Because if you compensate already the gravity there at the center of mass, it means that it's already compensated the gravity that is experienced every link, no? Because if you move the link, then your center of mass is moving, thus that wrench is also different, no?
So we think that these two equations are like this. So they are living together. Let's say there is no acceleration. So you have the gravity of the robot that is related to, here now you have all the contribution of all the links, and you have the total mass. And here you have a total gravity that needs to be sustained by the contact forces. So the contact forces, when you map to them, should have the total gravity of the robot. So you need to compensate, should fit the total gravity of the robot. Then this term is to consider the fact that the torques are not exactly the contact forces. It's a kind of, I know, it's a kind of tricky to think, and it's not very clear. I will think a better way to explain this, but for some reason this you know that this term takes account the fact that the torques is not directly the contact force, but it's like the lag model. So
because if you make zero that the WF decay, so let's say like your wrench is only to compensate the gravity, then you multiply by JB, you know, you transform that into external force, then you multiply again by the Jacobian to send to the torques. In that way you are compensating gravity in each link, no?
yeah, but
Could we think about the gravity compensation at the joint level to maintain certain posture and possibly at the base it is for the task that we do?
so
But the gravity one, only one. You cannot compensate two times.
yeah, I will investigate this. It's a very interesting
It's
point.
on that, let's say, the similar case. Let's say if you have your base on the ground and your leg up on the air, actually using the say normal gravity compensation will compensate just the gravity on your links, on your legs. While once you have your legs on the ground, you are not compensating for, let's say, the mass of your trunk, and you are just compensating the gravity of your links with the, let's say, lower part of the equations.
But this is a good point. We could say that this is just the gravity of the trunk, of the base,
More or less,
and this is the gravity of the links.
But
this one also contains somehow
because in the transformation you take into account the inertia of every link and also the transformation. So actually you are compensating you are seeing which gravity is experienced every link. Because in the transformation, the GP that you do, you have the inertia of every link, right?
Yeah. From my experience, I noticed that if you don't put this term, you have problem. You have errors. So you don't have you don't manage to track, to have zero tracking error. That's why. But it's a good question. This term doesn't have only the gravity of the trunk. There's also the gravity of the link. But in this term, we also the gravity of the link. So it looks like we are counting twice. But it's something I always was questioning myself. It works in numerical sense, but the reason why I need to investigate more. I will think about that, and maybe I write an email about this. This is a very interesting question.
So the approach that works is putting here the total gravity. I mean, m is the total mass of the robot. So
Yeah.
Okay, so everything, and then once we've computed F, adding again sort of gravity compensation at joint level.
Yeah. Yes.
Short question. Excuse me. Okay. So I wonder if this computation is in the planning stage and the last compensation is in the control stage. Okay, to be specific, because this WD is actually the desired range that we want to generate the desired motion of the system. Okay, so I suppose this is in the planning stage. We have a planner on top of the controller, right?
Yeah.
Okay, so that computation on the top is actually in the controller. It's in the control stage.
Which one?
The last one. The last one on the last page. Yes, on the previous page.
On the previous page.
Yeah, that one.
This one.
Yeah.
No, this is. I mean, the controller. I would say it's both of them. They are just the first stage that does the mapping from range to contact forces, and the last stage that does the mapping to the torques.
Okay.
So it's a kind of, remember the coupling of the floating base and the actuated part. So it's very similar. The first stage deals with the central dynamics, let's say, with an under-actuated part, finding the forces to desired motion of the central mass over the base, and the last part computes the torques to generate this motion, to generate these forces. So there are two steps.
Yes. So I want to say that because in the planning stage we just use the central dynamics. So I suppose there should be some compensations. But in the control stage, to generate the torque for the whole body, so we use the whole body dynamics. So there should also be some kind of computation. So I suppose it's reasonable, or I don't have specific ideas, but I suppose it's reasonable to have two compensations, but I just don't know if we should compute it like this.
What do you mean computation?
Compensation.
Compensation.
Yes, compensation. I'm sorry.
Of what?
For the deviation of for the deviation of the center mass, for the.
Yeah. I mean, this is like here. This is like an attractor. It's like a virtual spring. So if I have a desired trajectory coming from the panel, but if the actual COM goes away because of a push, then it creates an error in the virtual spring and then this filter spring create a force to attract back to the trajectory. So the compensation is not here, it's inside the feedback controller, maybe was not clear, it's inside the virtual model. Here. This is actual COM or actual base position. This is desired base position, and this eliminates, tries to eliminate the error. Okay. So this is, I agree. The controller, in a sense, the feedback controller is the very first step. Compute the virtual impedance. Then you have the mapping to contact forces, and the third step is mapping to torque. Good observation. Yes, it was not clear. So if you define it in the CM frame, the closed loop CM frame, you directly compensate the gravity this way. You don't have, you have a pure
Shouldn't
force.
that be negative, the range from the gravity?
Now this is minus 91. So you want to do plus. It's a positive
you're taking
number.
negative acceleration, because I think that the okay.
No, sorry. This is 1981. So it's a positive number.
But you want to.
Gravity is minus 800 Newton. You want to add plus 800 Newton. So it's a positive number. Why do we need a regularization? We said that JB transpose is not squared, exists a null space, therefore the solution of this is not unique. And we can see that because the action, if we compute the action of the QP without this term, it's positive semi-definite. Because you have something something like this, and if you compute it, you will see that you have some zeros popping out. So the action is not like that. The action, it's a really yeah, something like this, and you have efficiency. So you add this term to regularize, and you get a unique solution. And in that case, the action becomes positive definite, because you have like a diagonal matrix that you can set, I don't know, as an identity, for example. And according how do we shape this diagonal matrix, W, we can have different solutions. We can exploit, for example, the force redundancy. I will recall quickly what we said in the last lecture, that we can only apply the torques on the degrees of freedom. Part of the torques will generate some motion, part of the torques will generate internal forces, so no motion, and this depends on the kind of contact constraints and on the rank of the JB matrix. And in the case of 6, for example, and 6 columns, then we have no redundancy, while whenever the rank is 6 but we have more columns, then we have force redundancy. And in this case, I think this is still transpose. And in this case, for example, this is the case of a robot with 3 legs on 4 legs on the ground. You can use these internal forces to have different solutions. And in the case of W identity, we get the minimum norm solution. So we get something like or vertical, because this is the minimum norm solution of the force vector. While if you want, for example, to minimize the torque, then you can define this other weighting matrix. So let's replace to see what happens whenever you use that. F transpose J C Q or J omega tau, W tau, J F. In this case, you see that this is tau, and this is tau transpose. So we are actually using this weighting matrix, finding a solution that strives to minimize the torque vector, right? And with this other selection matrix, we can decide to penalize selectively the torque in some joints. So, for example, what does it mean trying to minimize the torque? That the contact force tries to go as much as possible close to the joint axis, So if we use, for example, in the tau leg, omega W tau leg, a big penalization for the knee joint, you will see that the contact force will try to be close to the joint axis of the knee. While if you penalize the hip AA joint, which is the hip adduction abduction, then you see the contact force will try to be close to the hip AA joint. Finally, you can see, you see different normalization. The next one, it's the cone normals, that it tries to put the forces in the middle of the cone. And now a different solution that try to minimize the torques. It's finished. And we saw that there is a third minimization that we can do, regularization, that allows us to improve the robustness of the contact. So if you look at these two situations, no? The robot climbing, walking through the chimney, what is the most robust situation? Why? Why the right hand?
Because it's in the middle of the equation, so you have more freedom to move outside without sleeping.
Yeah, so here the friction cones are satisfied, but they are very marginally on the boundary. They're satisfied very on the boundary, while here they are well inside the middle of the cone. So this situation is not robust, and this situation is robust, is what we want. In particular, why having the force in the middle of the cone improves robustness? Because we can have two kind of uncertainties whenever you have friction cones. One uncertainty is the friction coefficient. We don't know that. Who tells us? We can have semantic information. We see that there is high stroke with pair. We can set 0.2. I don't know. We see some rocks. Then we can say maybe it's 0.9. Who knows? There is mud, we don't know. So this is an open problem in robotics. How do we estimate friction coefficient? There is my paper, but we never try in experiment if it works. So and it works only if one leg is sleeping and not more legs sleeping at the same time. Then there is estimation of the terrain normal. So the cone has a certain inclination, and usually the terrain normal is estimated through either through vision. So you need to have an accurate map. You need to compute the derivative of this map, and then you have the unit vector that represents the normal, that is averaging 3 voxels, 5 voxels, 8 voxels around each point, and gives you a normal. But look at the quality of this normal, and I'm sure I am afraid to use them in a controller because sometimes they are just like this, you know, it creates a cone like this. So what I do normally, I use my nice terrain plane estimation. I fit a plane through the stance fit, and I say that is the normal. Of course, it's wrong, because if you are on a ramp, do I have a fence that works? No, I don't. So if you think about you are on a ramp, and you're a terrain plane, you have the 2 feet, front feet are on the ramp and the back feet are still on the plane. In the terrain plane is like this, so you estimate a normal like this. And you use the same for all the cones, but you see here the normal you use, it's different from the normal you need. And in that case you could have slippage. That's why normally you use a smaller friction coefficient, conservative friction coefficient in your controller with respect to the one that you think you are facing in the environment. And to have this robustness implemented, in essence, we consider the contact frame, and we build the rotation matrix between the contact frame and the wall frame, which are the unit vectors of the 3 axes, and then we normalize in this contact frame. This means that we define for each leg this weighting matrix that maps, let's say, forces in from the wall frame into the contact frame. Then you have again a weighting matrix to selectively normalize, minimize the tangential or the normal forces, and then you map back to the wall frame. Sorry. And then if you want to penalize, for example, the tangential component, this is what you're gonna do if you want to have the force in the middle of the cone. You set a high weight on the X component, a high weight on the Y component, and a low weight on the Z component. And then you stack this in a diagonal, block diagonal fashion for all the legs, and you have your W matrix. And these are some experimental results that I obtained with that experiments. We see here that this was the estimated friction coefficient. We did a very simple test applying tangential forces on that surface until the robot starts to slip, and measure the point in which they lose the contact of was the tangential force, and we found out that there was a friction coefficient of 1, and to be conservative we set a friction coefficient of 0.5, and we see that all the forces that are inside during the experiment remain inside the conservative one we set in the controller, and this conservative friction coefficient ensured a better tolerance to uncertainty in a normal direction to the surface, and tolerance on the estimation of this normal up to 18 degrees. So yeah, that was the presentation for the quasi-static approaches. Do you have more questions?
So on the friction cone. So for instance, if I'm right in the middle of the friction cone of the cone, it's very good for the stabilization of the body of the robot. For instance, if I want to hit the limit of the friction cone, and let's say, would I be energy efficient for some task in those cases? Because maybe, for instance, when you use optimization techniques, the reason that you add friction cone is not only to stay right in the middle, but also to go to the boundaries of the friction cone and exploit that, let's say, that value to do some dynamic motion. do you think that that could be an energy efficient, let's say, criteria for?
So depends what you write in the cost function, of course. When we use optimization, this is a regularization, so it doesn't mean that it will stay in the middle of the friction cone. If you're, you try to stay as much as possible in the friction cone, but if your wrench, if your motion requires a very high tangential forces, it will allow to find this tangential force. Just say, whenever you can choose a more robust one. But the nice thing of optimization is that it allows you to get to the boundary. Why? Because these are in the cost function and they are not hard constraints. So they normally they have a low weight. So with respect to the main task, that is, I didn't put a weight, but in the lab you will see, the main task will be predominant. So it is possible to reach the boundaries even if you have this regularization.
Because for, let's say, for dynamic motion, if the robot were to walk on the tilted platform, for instance, and if it has to do faster motion, I believe that if the optimization were to calculate the trajectory, might not have, let's say, cone constraint right in the middle or somewhere middle, but maybe at the, because it just needs to make a contact and disconnect very quickly and go to the another contact. So I think these are a kind of motion you can see in Alex Winkler's dynamic motion, where it doesn't need to stay on the contact for long, so it just touches it and uses that dynamic motion to.
Oh, in that case, you can put a very low weight on this. It doesn't matter. You can tune the cost function. There's no problem. So we have two things to do again. The last part of the lecture is the full dynamic task-based inverse dynamics with optimization, and the lab. Do you prefer to do the break now or do before the lab?
It depends how long is that.
I don't know.
I think now might be good.
Okay.
Because it will be theory again, so.
Yeah. Okay, let's do a quick break, 10 minutes.